Welcome to a SimCenter AIMSIM Student Edition tutorial solving a problem of machine dynamics and vibrations. The problem statement is that a loaded trailer with a mass of 1,000 kilograms rests on two wheels. Evaluate the behavior of the system if the suspension cannot compress further than 5 centimeters. Also, how do additions to the suspension and of wheels affect the behavior of the model? With the goals for the tutorials being building models within the mechanical library, performing studies to evaluate the vibrations of the system, and how to utilize simulation data to create the equations of motion for the system. The four-part series will include analyzing the proper amount of stiffness with no damping, then to evaluate the system with damping, next adding a pneumatic system to support the suspension, and then lastly evaluating the system with the addition of wheels and a road profile. For part 1, the undamped system's required stiffness is found, as well as the resonance frequency and equation of motion within these parameters. To determine the suspension's needed stiffness, let's establish first that the trailer's initial position, as soon as it is placed upon the suspension, is at 0, and cannot move further down than 5 centimeters or 0.5 meters. The trailer mass with the suspension stiffness will act in simple harmonic motion, being a sinusoidal wave with a peak to trough distance of 0.05 meters. This makes the equilibrium value of the system at 0.025 meters. Taking this equilibrium distance, trailer mass, and acceleration due to gravity, and by equating the spring force from the suspension as being equal to the force from gravity acting on the trailer, solving for the stiffness value to be 392,400 newtons per meter. To begin building the model, open the mechanical library and place a mass component in the sketch window, with port 1 facing upward for an easy visualization. Next, attach a linear connector node with a single port side connected to port 2 of the mass. For the other two ports of the connector, attach a spring and damper component to each, using the spacebar to copy the last selected component for the second port. The spring and damper remaining ports can be closed with a 0 speed source, and the remaining mass port can be attached to a 0 force source. Moving to submodel mode, Premiere Submodel is acceptable for all components. Once in parameter mode, open the global parameter window and create a real parameter with the name M, title, mass of trailer, value 1000, and unit kilogram. Opening the mass parameters, enter the global parameter M for mass, and change the inclination value to -90. This will make it so that the mass component's displacement is vertical, with positive displacement being upward. The stiffness value can be found within AIMSIM using the post-processing window, which if not available can be made so under Edit and making sure it is checked off within the Show/Hide menu. Create a new post-processing variable whose name and title can be ignored. The expression for the variable will be the equation used prior to solve for k, typing the letter M first and selecting the path referring to the parameter times 9.81 divided by 0.025. And after selecting the Update button, the value displayed is equal to what was calculated prior. Next, create another real global parameter with this value, the name K, and title Total Stiffness. Once complete, set each of the stiffness values within the spring and damper components to this K value divided by 2, and change the damper rating to 0. Afterwards, the model is ready to be simulated. After clicking simulation mode and compiling the model, run one simulation, and display the mass's displacement at port 1, seeing that the mass oscillates between 0 and 0.05 meters. When determining the resonance frequency of the system mathematically, let's begin by finding the angular frequency with the formula shown, being 19.8 radians per second, and when converted to hertz, is 3.15. Finding this value in AIMSIM is possible while in simulation mode with the taskbar above by changing the analysis from temporal to linear by clicking the button shown. Linear analysis will also be listed with a new drop-down menu available. In order to perform a linear analysis, linearization times must be set in the first option of the drop-down menu. Within the menu, times can be added and removed with 0 already being present. Because the model's behavior is linear already, the time selected is non-consequential and can be left as 0. Select OK and run another simulation. Reopen the linear analysis menu and select the eigenvalues option. Here, the eigenvalues and time constants can be analyzed for a system for different times, which for this case is only for the 1, 0. The displayed oscillating mode is equal to the calculated value in Hertz and can be changed to radians per second in the bottom right. The equation of motion for the system includes mass, stiffness, and damping, which is negligible. Plugging in these values and solving the differential equation with Laplace transforms, a time response equation can be found. Initial conditions of a displacement of 0.025 and 0 velocity are required, and then, with isolating the x of s and utilizing the cosine Laplace identity, a solution can be found in the form of a sine function. Because of the system in AIMSIM having an equilibrium value of negative 0.025, include that value to find the accurate equation shown. The calculated time response equation can be validated against the AIMSIM model behavior using a function block from the signal and control library with a clock source fed into the component, making the simulation time the independent variable. The output of the block can be fed into a signal sink. Moving to parameter mode, enter the equation as an expression in terms of the input x, and move to simulation mode to perform one run. Compare the results plots for the displacement of the mass to the output of the function to see that they are perfectly even. And with this, concludes part 1 of the demonstration. Thank you.